Okay, hi, I'm here to talk to you about energy mass equivalence. Basically, Einstein's well-known equation E equals mc squared. It's pretty simple and straightforward, but has really profound consequences on the world around us. And the idea is this, is Einstein realized that energy and matter are equivalent, meaning that energy can be turned into matter, matter can be turned into energy, they can go back and forth, and in fact, it's probably happening all the time in very, very small amounts. But in the bigger scale, it doesn't happen too often on our planet, but at the same time, it's really what powers our world, because nuclear fusion, which is what happens to in the sun, fusion is molecules combining. So light stuff combines to form heavier stuff, fusing together basically. And this is what creates energy. Just a little bit of mass is lost each time this happens, but that little bit of mass becomes energy, and that energy is radiated as sunlight and powers our world. If the sun wasn't shining, then we probably wouldn't be here. On a different level, you also get into fission. And fission is what happens when you have like a mushroom cloud, an atomic bomb, but also in nuclear reactors, is that in fission you take heavy elements, turn them into light elements, and again, like, there's this range of what elements you can use, but in fission you take heavy stuff, you know, like uranium and plutonium and stuff like that, and it becomes something lighter, and as it does, it loses just a little bit of matter, and that little bit of matter becomes energy. It turns into energy. And it can release potentially a lot of energy, because in this equation, E equals mc squared, c stands for the speed of light in a vacuum. And the speed of light in a vacuum is 3 times 10 to the 8th meters per second, and it's squared, so c squared is 9 times 10 to the 16th meters squared per second squared. It's a big number, so it doesn't take a whole lot of mass to get a lot of energy, and the energy you get from this is going to be in joules. Same joules that we used before. It's a scalar quantity, for example. And a joule is equal to a kilogram meter squared per second squared, which comes straight out of this equation. Kilogram meter squared per second squared, meter squared per second squared. So let's just take something, you know, kind of a manageable size. Let's say you have a textbook, and that textbook is, you know, even if it's a big textbook, let's say a big textbook is 5 kilograms, which is more than 10 pounds. It's pretty heavy, right? And it all turns into energy. So E equals 5 kilograms times c squared, 3 times 10 to the 8th meters per second. That whole thing is squared. So you end up getting 5 times 9 is 45. Change it to scientific notation, 4.5 times 10 to the 17th joules. That is a huge, huge amount of energy. Certainly equivalent to like atomic bomb scale type of thing. So if you had all that energy being released in a short amount of time, it would be very, very devastating. So you can imagine that, like, even if you took something much, much lighter, like, let's say you took 0.5 kilograms, that's 1 pound, that's an apple. Let's take even less than that, 0.05 kilograms, something very, very small. You would get 4.5 times 10 to the 15th joules, which is still a really big number. So small objects can create a lot of energy through this process, which is why small amounts of matter in the sun create lots and lots of energy. And it's an equation that you are all familiar with, and hopefully you know a little bit more about now. I think that about does it for this particular video. Thank you very much for watching.